Okay, so let's start. I think my screen is visible. Yeah, hopefully it's visible. So last time we defined something called the polychromatic number of the plane. So let me go through the definition again. So this problem asks something very related to the chromatic number problem. Um, this is recap. What's the minimum number of colors needed to paint the plane so that no color realizes all positive distances?
Realizes means obtains, right?
Yeah, so basically, when I say a color red realizes the distance 0.5, that means there are two red points whose distance is 0.5. So
Okay, fine.
in other words, so you suppose you color the plane with 5 colors. So for every color, there will be some real number, say 0.25, so that there are no 2 points of that color exactly with 0.25 distance. And this minimum number is the polychromatic number of the plane, which I've been denoting by the notation pi p. Sorry, this is chi p. So last time we showed Rice-Key's proof. Well, it's not actually Rice. Let's not get into whose proof this is complicated history behind this. But we saw a proof that I agree is at least 4. So you cannot color the plane with 3 colors so that this thing happens. So today what we're going to do is we're going to look at some upper bounds and sort of connect the problem of finding upper bounds to our previous problem with Heidegger and Nelson. So yeah, someone is trying to join. Okay, yeah. So this is what we're planning to prove today. So of course, to do that, we have to the strategy is to exhibit a explicit coloring of the plane, and as always, the main idea is equilateral triangles. So I don't expect people to come up with this coloring unmotivated. This is fairly clever. So I'm just gonna show you the coloring. Yes. So effectively, we split the plane in these parallelograms, and inside each parallelogram there are 4 hexagons and several 8 equilateral triangles, and they're colored according to how the numbers are there. And this side length is 1. Now, of course, we need to verify that this actually works. So, and we also need to verify what happens at we also need to specify what happens at the boundaries. So let's say for every hexagon,
Sir, are these rhombus or parallelograms?
I mean, rhombuses are also parallelograms, so both are correct. Yeah. So yeah, where was I? Yeah. So we also need to specify what happens at the.
No, I'm asking, is this a parallelogram or a rhombus?
Yes, these are rhombuses and therefore also parallelograms.
Okay.
Yeah. So yeah. Yes, where was I? We need to specify what happens at the boundaries. So we just say that none of the triangles include its boundary, and for the hexagons, you effectively go something like this. every hexagon contains its entire boundary except its one rightmost vertex, just this, and these vertices. Yeah. So you should be able to check that this sort of uniquely determines the coloring for every point on the plane, and I'm not gonna go through the details, and for the purpose of simplicity we'll effectively ignore boundary issues for now. But what I want you to do is, so if this does satisfy the given condition, that means for every color there has to be a distance that it avoids. Can someone tell me what the distance is? So for example, for the color 1, what is the distance that it avoids?
2.
Explain.
Like the maximum distance in a hexagon is 2, and the 2 is not taken because of the boundary
Yes.
conditions.
You have the right idea, except I didn't call this side 1. I am calling this side a 1.
Oh, then 1.
Yes. But yeah, you have the right idea. So this is the distance each hexagon avoids. So
Yes.
color 1 avoids the distance. Let's make a table of sorts. Color 1 avoids the distance 1. Color 2 has nothing different from color 1. So of course, it also avoids distance 1. Same with 3 and 4.
Sir, are you writing something?
Yes, is it not showing?
No.
Huh. Okay. Let me try to fix that. Did that work at all? That didn't work, did it?
No, I think that a resharing will help.
That's exactly what I did though. Okay. Something is happening. Hold on. Ah, technical issues. Yes. I started sharing, but that didn't seem to do anything. Huh. Let me let me try rejoining this call from my tab. Something is definitely happening. Oops. Yeah, do you see the table now?
Yeah.
Perfect. So yeah, like I said, the colors 1, 2, 3, 4, they all they all avoid the distance 1. What about 5 and 6?
They avoid distance half.
That is correct. I mean, this is not hard to prove. Try to convince yourself if you haven't already. Okay, for some reason my tab keeps leaving a meeting. Verify. You are not seeing the writing anymore, are you? Ah, cool. Verify. Cool. Anyway, so yeah. So this effectively proves that this coloring does work. So which means chi p is equal to 6. But
So, sir, are we taking midpoints of the sides of the rhombus?
yes, these are midpoints of the sides of the rhombus. Okay, just to be clear, all these lengths that look like equal, they are equal. The hexagons that look like regular hexagons are regular hexagons. The triangles that look equilateral are equilateral. That should be enough information to uniquely determine the geometry of what's going on.
Okay.
So that gives us an upper bound, and this is the best known upper bound, so there's no improvement that can be done with that. But we can certainly try studying other colorings and other tilings that achieve the same bound and see if that gives us anything interesting. So to do that, we introduce type of a coloring. So suppose you color the plane with 6 colors, exactly 6 colors, and for each color you write down a distance that it avoids. So that's exactly what we did here, and we write that as a sextuple. So that sextuple will be called the coloring type of that coloring. So for this coloring, the type is, right? Yes. Now, remember, the problem of finding this coloring could be rephrased as find a coloring that has type this. And note that you can always scale things up by a factor of 2 or something. So a type of coloring, a coloring of this type is the same as a coloring of this type.
So what does it mean to write this, that coloring of this type? So every color has to avoid exactly this distance or at least this distance.
At least this distance.
Okay.
So one coloring could have multiple types, but that usually won't be the case. So no one cares about that. Yeah. So point being, scaling does not matter, but in general, we will try to maximize the number of wands in the tiling, number in the expression of the types. So for uniformity and for easier keeping track of things, so we will write the type of this coloring as this. Now, here's the question. Recall that we proved the chromatic number of the plane was less than or equal to 7. We do not know if this is less than or equal to 6. But suppose we were to find a coloring for that problem as well. Can you rephrase the problem of finding that coloring in terms of types?
I think 1111 6 times.
Yes. So if we manage to find a coloring of this type, then we would have gotten a little closer to the solving the Hadwick and Nelson problem. Of course, we won't because that's an open problem. But the thing to keep in mind that in general, it's a good idea to try to maximize the number of wands in the type of the coloring that we're looking at. So this coloring has 4 wands, which is pretty good, but and this has 6, which is at present impossible as far as we know. So a natural next step would be to look for 5 wands, and this will be some other real numbers, say alpha. So clearly, in some sense, a coloring of this type is better than the coloring of that we just saw. Yeah. So let's look at some 6 coloring of this type. So we happen to know a coloring that has the type. Well, I'll let you verify what the const. Actually, that's probably just boring computation. I'm just going to tell you. Yeah, and that coloring is given by this. How do we make this diagram? We first, yeah. We first start with 2 squares. This with side length 2, and another small square right about here, which has side length 1 over root 2. Now, if you chop off these squares from every corner of this bigger square, you will end up with an octagon, right? Yeah. So this octagon is what you see over here. And these squares are these little squares. And there's the issue of the boundary points, of course. So, I mean, yeah, I'm not going to go into the details of that, but you can verify that this coloring does work, in fact. And I have not. So in this diagram, the octagons have the colors 1 through 5 in the order that we have shown, and these squares have the color 6. So if you actually do the calculation, you will see that the octagon, the color 1 avoids 1, 2 avoids 1, and so on. And the color 6 avoids 1 over root 5, which is something which is pretty good. Yeah. Here is one more coloring which gives a type of this form. It's this rather pretty looking coloring. So yeah, let me give the dimensions of this thing. This square has side length 1, and this square has side length root 2 minus 1. Yeah, and this coloring does work out if you calculate the dimensions and everything. So I'm not going to do that, but I want you to sort of calculate what the type of this coloring would be. So first, to start with, figure out what distance the color 1 avoids, what distance the color 2 avoids, and all the way up to 6. I mean, if you get 1, the rest are usually not different. I'll give you guys a few.
So could you repeat once?
Yes, so I'm looking at this coloring right now, and the dimensions are as follows. This length is 1, and these squares have side length root 2 minus 1. And I want you guys to figure out the type of this coloring. I claim this is a coloring that satisfies the polychromatic condition, and I want to find out what distance the color 1 avoids, what distance the color 2 avoids, all the way up to 6.
1 to 5 avoid root 2.
Okay.
Like if you have appropriate boundary conditions.
Sure. Let's just ignore the boundary conditions for now. They are kind of important, but we will ignore that for now. These avoid root 2. Is that what you say? Sure, that sounds reasonable. What about? Wait, does it?
6 avoids 2 minus root 2.
6 avoids 2 minus root 2.
So if
Yes,
you divide everything by root 2, then you get what we want.
yes. So if so, the type of this can be written as this, and if you divide everything by root 2, we get this. So this is the coloring that we're looking at. Sorry. Yeah, so this is the type of the coloring we're looking at. Make sure these calculations make sense to everyone. If it doesn't, just stop me and I'll go through the details. So yeah.
How we got that 1 by root 5 didn't make sense to me. Like,
But I was hoping to avoid that. But yeah, let's see. So what do we have here? So yeah, let's try to figure out what sort of distance this avoids, right?
like from where did I don't know. I don't think 5 can ever come in the calculations.
No, 5. There will be some sort of 2-1 triangle at some point. The right triangle, like here's 2, here's 1, and here's root 5. So at some point that will be there, but let's just do the calculation, right?
One can't avoid one.
Sorry?
One can't avoid one.
One can't avoid 1. Why not?
Like because dimension of the square are 2. So
No, I mean, this is after appropriate scaling. So what
Oh.
distance does one avoid? Can you tell me that? I really don't want to do the calculations. So effectively, we want the distance from here to here. Is that it?
I think 1 avoids the distance 2 if we take care of the boundaries.
Let's just ignore the boundary issues for now. Okay, I'll let you guys, some of you calculate the distances for this one too. I know I have been asked the question, but I'm too old to do calculations at this point. So someone said 1 avoids the distance 2. I'm going to believe that. What about 6?
I think 1 over root 5.
Yeah, that actually sounds more reasonable. Can you just
Like,
which distance are you calculating? I know it's hard to point out
in
things from.
octagon, like the diametrically opposite points.
Yes, like this and this, right?
Not that, like inside the octagon
Acha, I
actually.
see.
Like one octagon.
Right. Yeah, that makes more sense. Yeah. So yeah, so this is 2, and this should be 1, hopefully.
Yeah.
This is indeed 1 because you're taking out half and half from here. This leaves us 1. So this is root 5. And what about the sixth color? That's just this distance or this distance.
Yeah, that is just one.
That is just 1. So yeah. So the type of this is root 5s and a 1, which is after proper scaling is 1 over root 5. Cool. So that calculation makes sense, hopefully.
Sir, after the class, could you send the notes of this and the previous classes too?
Sure, I'll do that. Some of the notes are a bit, I mean, scratchy. I don't know what what you're gonna interpret from this mess, but sure, I'll send the notes. And I think at the end, I'll also send some resources for these things. So if that works for you, even better. Anyway, so where are we? So we were looking at colorings that give types of the form 1 alpha, and we have found alpha equals root 2 minus 1 works. Alpha equals 1 minus root 5 works, and a natural
In
yes.
alpha
Go
equal
on.
to 2 minus root 2, which distance do we calculate?
So root 2 minus 1 came from this tiling, right?
Yes.
So
So 2
we
minus
are
root 2 came from this. And
yes,
then we scaled.
we scale down.
Yeah.
So does that answer your question?
Oh, which distance do we take in that figure?
So yeah, root 2 was from, okay, so root 2 was from, where was root 2 from? Yeah, root 2 was from the maximum distance between this and also the minimum distance between this. They both should be root 2 if I did things right. And
Yes.
the root 2 2 minus root 2 thing came from the maximum distance between this and this, which is also equal to this distance. All right. Okay. So like I was saying, it's worth looking at what all real numbers, what all positive real values alpha can take in this. And in fact, so let's give that set a name, right? X6 is all possible values of alpha. So if 1 was in the set of all possible values of alpha, if 1 was in the set X, then we would have solved, would have been made some progress towards the Heidegger-Nelson problem, but we do not know this. We do know that root 2 minus 1 is in X6, and 1 over root 5 is in X6. And we actually know quite a few numbers that lie in X6. Any guesses as to how much we know? I mean, how many numbers are known to be in X6?
Maybe all numbers less than one. Not sure.
All numbers less than 1. No, that is actually not true. But in fact, it's it's a surprisingly large set. In fact, this entire interval is known to be inside S6. So that's a lot of numbers, uncountably numbers, in fact. So to prove this, we will need to find the general construction that takes in any alpha in this range and spits out a possible tiling, which is sort of complicated. So let's try to do that. So remember we started with this configuration, right? We took a square, some side length, and sort of symmetrically plopped a square onto its corners, and things sort of nicely worked out. Yeah, go on. If someone's mic is on, do you have a question? Okay, I guess not. Anyway,
It was by mistake, so.
no problem, no problem. Anyway, so to get the 1 by root 5 bound, we essentially started with the square and plopped two squares on its corners to get this octagonal thing. Now the trick is we do the same thing, except instead of plopping the square symmetrically, we sort of take a skewed tilted version of the square and cut off its corners with that.
But I think to prove the root 2 minus 1 bound, the construction we made was very weird than this.
Yeah, what
I think for the root 2 minus 1 bound, we did a very different construction.
no, so yes, for the root 2 minus 1 bound, we did do a very different construction. So, well, if you look at it, it's technically a lot similar. You have the central square, and these squares, they don't cut inside the square, but they are sort of stacked onto it. So you will see where this comes from, how this comes from that. So for the general case, what we do is we take sort of tilted versions of the square and put them in here. So if you do this symmetrically, you get the 1 by root 5 construction. And if the tilt goes all the way, so the square sort of sticks on its side, then you get this. Does that make sense?
Yeah.
Yeah. So now we need to figure out the details of this construction. Yeah. So if you size the squares appropriately, you get a tiling that looks something like this. And
What is the size of the small square?
yeah, so that depends on the situation a little bit. So we have to adjust. We will do the adjustments at some point, but this is how the tiling looks like for now. We will get there. Hold on. Where was I? Yes. So we need to choose the sizes of the things properly so that this color forbids, each color forbids some distance. So let's do that. So this was a bigger square, and we plopped a square about here. Okay. So let's call this distance x, I guess, and this distance, let's call that y. Giving things name is always a good start to solve the problem. And so here's the thing. We need to figure out what possible ranges of values x and y can take so that the tiling induced by this configuration actually forbids some distances, right? So, which feels like a humongous amount of computations at first, but we can sort of simplify the issue by some clever tricks. So let's try that. This was y. Let's sort of split this into squares. Yeah. So what do we want? First of all, recall our coloring. So suppose we want to find the distance that's forbidden by 1 and 1. So what's the maximal possible distance inside the inside this square, which is colored 1, that's just this length. Yeah. And we want that to be smaller than the minimum possible distance between these two things. Well, terrible diagram, but yeah, these two things, this one and this one, which is in fact this distance. So let's call this D1 and let's call this D2. So what we want is D1 has to be bigger than or equal to D2, and yeah, and we also want these squares are colored with the sixth color, right? So we also want these to forbid certain distances. So let's figure out what distance that is. So the maximum distance between each of these squares is just the diagonal of this. Let's draw that here. This diagonal, let's call that D4. And we want that to be smaller than the minimum distance between two different squares colored with the sixth color in it. So D3. We want these two conditions to hold.
I think we want D3 less than equal to D4.
No, I want D3 bigger than or equal to D4. So every distance under D4 is achieved by points inside this small square, right?
Hmm.
And we want something, so we want, how do I put this? And D3 is the smallest. So suppose the distance between these 2 points is 1, and if the distance between these 2 points is 1.2, then I can say that the distance 1.1 is not achieved by any of these at this particular color, correct?
Yeah.
So we want this to be bigger than this, and equal would also work, but then we'd have except we'd have to be careful about the boundary issues, which I'm ignoring for now. Does that make sense?
Yes.
Okay. So this is what we want for now. Yes. Now, can someone calculate the expressions for D1, D2, D3, and D4 in terms of X and Y? This is a student computation. Let's start with D1, I guess. So what is D1? D1 is the distance between this point and this point. And how should we go about calculating that?
Maybe we don't calculate its exact value. We just want to prove it's greater than D2, and that doesn't seem too hard.
We don't, we can't actually prove this is greater than D2 because we need to fix X and Y so that these inequalities do happen, right? And from that, we will also need to calculate alpha.
Okay.
So the exact expressions are sort of important. So to just to shove you on the right path, to calculate D1, you basically need to figure out the horizontal displacement between these 2 points, which is this plus this, and the vertical displacement between these 2 points, which is just this length. And to zoom in, note that this length is X, this length is Y, this length is also Y.
How?
Because that's how we sort of wait. Yeah, sorry. So that's how sort of we set things up, right? These squares are cutting off. Oh, so I haven't quite explained that part, I guess. This was a bigger square, and since this cuts off a square, a triangle like this, that lets us sort of partition this whole thing into pieces. Yes. All right. All right. This length is one. You will need at least one length to start with, except there's nothing to do. Probably should have started with that. You need the distance between this point and this point. It's different names. So, any ideas so far?
Have you proven that x and that thing?
Have we proven what?
You said that the distance between A and this parallel line is x. Have you proven that?
Uh, this distance you mean?
Yeah.
Okay, that's sort of obvious from symmetry, I guess. But I mean, you can try to prove that. But you can assume that these four triangles are all equal. This. So this is sort of like the high school proof you see for Pythagoras theorem, right? And these four triangles are all equal. And this triangle has sides, legs x and y. So does this one and this one and this one. This technically does require a proof, but it's obvious from symmetry.
Or we can join AB and it passes through the midpoint. Then we have this length x, and then we can
Yes.
calculate this, or you can say
Uh,
perpendicular.
so we need this length.
Yes, and then we can double it.
Yes, correct. So what would this length be? So we know this length. Do we know this length?
Y minus x.
Y minus x.
That's correct. So this is y minus x. So this total length is 1 plus y minus x, which means this, which is half of that, is this thing, this nonsense. And this is known to be x. And when you do the calculation and double it, you will get d1 is well, yes, everyone agrees with these calculations.
Yeah.
Okay, let's try d2 next. What was d2 again? D2 should be easier. D2 was the distance between here, C to D.
Oh, we can like just drop perpendicular from C onto this bottom line.
Uh-huh,
It intersect at this square, and
uh-huh.
so this distance is 1,
This
and
distance is 1. How
yes,
about this
no,
one?
this is like inside the square. It seems to be y by 2 by symmetry inside the square.
Uh,
I think it's just 1 minus 2x.
that is correct, because from this entire horizontal direction, you are cutting off this part and you're cutting off this part, right?
Oh, okay, yes,
Yeah.
yeah.
So this is 1 minus 2x. These still look pretty bad, but we'll see what happens. D3. What was D3? I forgot what D3 was. Did I even draw D3 on the diagram? D3 was this distance, yes. Now
This
this
is
was
just 1
1
minus
minus
x.
x minus y.
correct. And finally D4.
D4 was the diagonal one root x square plus y square.
Sorry, say that again.
Root x square plus y square. Oh, okay, sorry. I
Into
missed.
root 2.
Into root 2, yes, that is correct. So twice of that. Yeah. So let's just write down inequalities that we have so far. We have these are still looking fairly bad, but we'll see. Maybe things do get better. So the obvious next step is just squaring stuff. Yes. Now at this point, I'd like to like sort of expand these things out and simplify these. And if I was a student and I was in a class, I'd hate for the teacher to assign this problem to me, but I'm gonna do it anyway. So can someone do the simplification? Because if you okay, to give you some incentive, I promise if you do the calculation, something cool happens.
So like will things factorize or something like that?
Hmm. Let's find out. Let's not factorize stuff. Let's just expand these things and write it as polynomials in X.
The first one gives x square plus y square minus 1
Minus 1,
plus twice x plus y minus xy
x plus y minus xy.
greater than or equal to 0 if I didn't do anything wrong.
Yes, I think that is correct. Yes. So I'll just restate since I want things to be in polynomials in X. I will
I
just
think
is
the
x.
coefficient of x should be -2.
coefficient of X should be minus 2. Is that it? Why?
Oh yeah, I messed up. Sorry.
Yeah, so the X squared, yeah,
It
I
is
think
just
this is
x.
correct.
It is x plus y minus 1 whole square, something like that.
Yeah, I think this is correct. This should be correct. So I'm just gonna rewrite this as quadratic in X.
It's a perfect square.
No, it's not a perfect
Oh, is
square,
all.
but almost, yeah,
I thought it was a plus
almost.
1.
So this is greater than equal to X. What about the second one?
So it's x square
Mm-hmm.
plus twice of x minus 2y plus y square plus 2y minus 1 less than equal to 0.
Okay.
So in the greater one, should I speak?
No. Okay, hold up. There should be a XY term somewhere. Wait, can you? Did I write what exactly you said?
Oh, I said it's x, like in the second and third term, just x times 2 minus 2y.
X times 2 minus 2y.
Yes, like
Yes,
in the
this is more like it, which is just factorable. So I'm just going to write this as yes. So if you're not asleep by this point, you will notice these and these are just opposites. So since both have to hold, this is actually an equality, which is the cool thing I promised would happen, but I may have overhyped the coolness of it a bit. Yeah. So that's an equation. And what this tells us is for the tiling to be a valid tiling that avoids colors in the right way, this equation has to hold. And that means for every value of y, we will get a fixed value of x that will give us something good. So this is a quadratic. So of course we can solve this in x. If you do the calculation, which I won't make you do because I've already tortured you enough, you get something like this. And so this gives a positive real value if and only if y is in this range. And but notice in our diagram, we sort of implicitly assume that x is less than or equal to y, right? So, and some of these values will give the other reverse direction of the inequality. So if you also factor in the fact that x is less than or equal to y and plug that in and do some stuff, that will give us a more stringent bound of again, I'm not making you guys do these calculations. Why would I? So what this means is, this is probably even better seen from a graph of all those things, but let's forget that. So what this means is, within this range, every value of y gives a possible x, and that specific x and y gives us equalities in these inequalities. And when you plug those in the diagram, that gives you a valid coloring with possible issues at the boundaries that which can be resolved. um, I mean, this needs proof. This is, I'm just saying they can be resolved, but if you really want, you can verify yourself by verify that boundary issues can be resolved. Yes. So yeah, so that is pretty cool. And what type does this coloring have? We want to figure out what the value of alpha is in that type of this thing, right? What type does this coloring have?
So we have to calculate the ratio d3 by d2.
We have to calculate the ratio d3 by d2. That is exactly correct. So in the sense that the color in this side, the bigger square, avoids the distance d2.
Oh, sorry,
And
d3 by d1.
no, I think, well, you're right. D3 is equal to D4 and D1 is equal to D2 anyway, so it doesn't really matter. So you're right the first time too. Okay. Yeah. So this color avoids the distance D2, and the smaller squares, the color in the smaller square, they avoid the distance D3, which is just happens to be equal to D4, and which means the type is D2, 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 D3 or D4. And when you divide stuff and put all ones in here, you see that alpha has to be equal to D3 by D2, right? So what range of values can alpha take from here? Now, yeah. Now the trouble with figuring that out is the expression for D3 and D2 are kind of not good. Uh, so if exercise calculate the range for D3 by D2 from here. I'll give you a brief sketch of the proof. So what you want to do is you want to introduce this new variable capital Y, uh, because there are tens of square roots in the original thing, right? So you sort of want to get rid of that. And also d3 by d2, d3 is square root of something bad and d2 is square root of something bad. So what we want to do is actually calculate the range for alpha square. So that gets rid of these square roots. And when you plug in the value for x, which from this equation, you get still more square roots. So get rid of that, you introduce this new variable y and figure out where y varies. And you figure out an expression for alpha square, which will turn out to be something like,
How the square roots cancel?
the square root don't cancel. This is terrible notation. I'm sorry. So we know alpha is d3 by d2, which is square root of something, square root by something, and dealing with square roots is bad. So we might as well figure out the range for alpha square. And if we do that, d3 square by d2 square, that expression won't have that many square roots anymore. So that was a terrible way of putting that. Thank you. Yeah. So you make this change of variable and you find out that alpha square will turn out to be, if I did my calculations correctly, still not great. Uh, sorry, I did something wrong. 32y is 20. Now, this is still not great, but this is like a rational function. We have techniques to deal with stuff of the sort. And in fact, the denominator is not as bad as it looks. You can sort of simplify that to, I guess, 1 minus 2 4 power 4 plus some constant. I think that would be 4 or something. Yeah, 4. So if you do the calculations, you will find that alpha varies inside the range root 2 minus 1 to 1 by root 5. And that's it. That's our proof. Yeah. Any questions so far?
How do we deal with rational functions?
Rational function. So you may have done all those things in high school, right? The things people do with, what are these things called? Okay, actually, shouldn't need to use that. So if you make another change of variable here, so if you replace, let me just spell out the details anyway. I mean, how we deal with rational functions is a very general question, but in this particular case, the expression for alpha square becomes yeah. So this. So and we know what range z varies in, and you can sort of take the derivative of it to see where it is increasing and where it's decreasing, and that sort of lets you figure out what range it takes.
Like alpha square is 1 plus something positive. So how can it be less than 1? How can alpha be less than 1?
Because z can be negative. Z can be negative. Z is y minus 2, remember?
Oh yeah, got it.
So yeah. In fact, I think z would vary precisely within the negative. The range for z will be something like this. Actually, calculate that yourself. I'm not going to give it away if you want to, or you can just trust me and not do the calculation. That's what I would do if I was in your place. So yeah, if you calculate this out, you will find that alpha varies within the particular region, which means we get a whole range of values for which we know tiling of this particular type, which is pretty cool. And that's where I'll end for today. So any questions?
Can we prove that all alpha not in that range and do not satisfy this?
I cannot. I don't think anyone can. This is still wide open. I think some specific real numbers are known, but I'm not very sure about exactly which ones.
I mean, if we prove that, then chi equal to 6 won't work, right? Because 1 will
Yes,
also
that is also true. If we do prove that, that will in fact prove that there is no coloring of this type, which would be fairly good. So yeah, I can't do that yet for you. I'm sorry. Yeah. Any more questions? Yeah.
Thanks for the lecture.
Yeah, sure. Okay. So this is our and for today. Tomorrow we'll look at a very related problem called the odd distance problem. So your assignment for today, if you choose to accept it, is to figure out what this problem should be. I mean, you just know the name of the problem. That shouldn't be enough info, but you should have a fairly decent idea what the problem should state and maybe work on it. Maybe discover something. I don't know. Feel free. Go nuts.
And can you please send the notes?
Yes, I will do that after. Okay. So yeah. See you tomorrow. Bye.